Okay, thank you so much for coming. Thank you so much for joining me for this journey through topology. Yeah, so let me remind you what we have seen last time and where we left off. So what we are studying right now, what we're trying to study are those surfaces. Essentially, this is a good picture. So what is a surface? A surface is something where locally you have a neighborhood that is some form of a disk. Topologically, a disk could be a heart-shaped patch on your pair of pens. And we are trying to kind of understand those surfaces. Eventually, we would like to write down a classification. Classification just means we want to list all of them. Okay. Seems to be, I don't know, quite a demanding task. So we have seen several examples of such surfaces, and some of them look really nice. Clearly, it kind of makes sense to study them. They appear somewhere in nature. The soccer ball, hexagons and pentagons. Let's say the pentagon itself is disk neighborhood of a point. So it's a pretty standard example, or maybe the example of a surface. A little bit more sophisticated, the object down here, but it still appears in nature. And then we kind of seen a little bit more difficult spaces, and it was not quite clear how to think about them, like the projective plane. If you have seen the projective plane in geometry, where you essentially identify lines, so because you identify lines, all I'm saying is we can just fix them to be of length 1, the corresponding vectors. You identify vectors on the same line, so we can just fix them of length 1, and then they lie on our little sphere, which is kind of normalized to be of length 1. But we would still need to identify opposite points because they still lie on the same line. And we end up with a surface, and everything goes through. So we have a disk neighborhood, which is just always mimicked on the other side. If I move it along here, well, that's the surface. It absolutely has no reason to turn up in real life, and it doesn't. So this is really weird. We will see that it doesn't later on, when I will tell you that this essentially wants to live in 4 space. So we kind of can't see what it is in 3 space. That's what makes it so hard to imagine. And we have seen other more complicated, also complicated surfaces, which also don't turn up in life. So we're kind of stuck with this idea of that something really simple. We just locally study kind of objects which are disks locally. So locally, they're all really easy. And what really matters is how they kind of look globally. Right? We have keep in mind my analogy with the Earth. Kind of locally, it's like a disk, like it's completely flat, looks like a disk. But how can I actually tell that it is actually a sphere and not something crazy like this beast here? And so we need some better way to understand what those things are. And today I show you an absolutely fabulous idea how to study those spaces, which is really, really simple in some sense, and it's also really, really beautiful. So yeah, hopefully it will be fun. Okay, and I also showed you some examples that not everything is a surface. So whenever you have like three sheets of a book, well, you can't really put a circle there, right? You can't really put a disk there. It will have 3 edges, three different pages. So it's not really working out. Anyway, now comes something. Oops, I was one too fast. Here comes the main idea. I write it down as usual in mass, and then we'll have a look at examples. The main idea is the following. Instead of studying a surface where all the complexity comes from its global structure, it's somehow easier to study the patches on the surface. Right? Instead of looking at the pair of pens, I look at the patches of the pair of pens. Yeah? So, and I think of my surface being decomposed into a lot of little patches, well, let's say 1 up to R, and I call this thing an identification space. If kind of there's a gluing rule, we'll see that in a second in like millions of examples, and a gluing rule on these patches, it kind of determines the surface in the end. Okay? So I really would like to think of the following picture. I have my little surface, and it's kind of very, very complicated, whatever it is. Locally, it has a disk, so I can just take a lot of disks together. So these are my XR, XI, and adjust a lot of them so that I cover everything. Okay, so I just put a lot of them together, and I add another rule. I just remember how they are glued together. Right? So I kind of cut my space into small bits, which are all very easy, and one extra rule, namely how they are glued together. Then I've kind of decomposed my a priori complicated problem into smaller problems and an extra rule how things are glued together. So a priori, that's always a good idea. Somehow you have a global problem and you decompose it into a local problem. You only need to kind of remember how things are glued together in order to get the correct surface. Turns out that this method is like extremely powerful for surfaces. And yeah, we'll see. So let me give you an example. So let's take the cylinder. Okay, so we could, and how can we find now this covering space, those x's? When I do the following, I do an operation which I told you I don't want to do, and you will see that the thing I get is not the cylinder anymore. So I cut the cylinder open, okay? I take the cylinder, and let's say I cut it here along this line, and I bend it open. I will have a nice animation in a second for you. Right? I cut the cylinder and make it open, and what I get is a piece of paper, just a rectangle. So that's not the cylinder. I kind of cut the cylinder in half. So what do I need to do? And that's the whole point of the definition on the last space. I need to kind of remember that I want to glue my cylinder along these two edges together. Right? This is my cutting edge. So my cylinder is glued together along this edge and this edge. And this little component here is the B one, and this little component here is the C1, right? So, and I'll show you an animation in a second, but note what I've done. The cylinder is kind of a slightly complicated object, and now we have just a piece of paper together with a rule how the ends of the piece of paper are glued together. So let me have a look at how this works. So let me do it the other way around. Let's start with a piece of paper. So this is just a piece of paper. And I add the rule that I want to glue the edges together, and let's see what we get. So I add the rule that I want to glue, in this picture, the bottom and the top edge together. And this is how it works. You take it in your hand, you take the piece of paper in your hand, and you bend it up until the edges are identified, and what you get is a cylinder, right? Let me do it again. Start with something that is much easier than a cylinder. It's just a piece of paper. And I have this one extra rule, how to identify the edges of my piece of paper. And I just say, OK, I want to identify the bottom and the top edge. And this is what I get. Right? So the information of having the piece of paper and my rule of what to identify is equivalent to the definition, to the having a cylinder itself. But it's somewhat an easier space, because I can just draw a rectangle and tell you what to do. And in other words, instead of thinking about a really complicated surface, we just think of a piece of paper and some rules how the edges are glued together. And that's just an absolutely fantastic idea. And essentially, our main point is to study surfaces along this, following this idea. And in this case, I only have one x. And it will turn out that I never need more than one x, so I can always just realize it with one piece of paper. But in principle, I could cut it even further into smaller pieces, and we'll do that. But here, we only need one piece of paper. And this is so amazing. I know I sound like a broken record, but I will just repeat it. Instead of looking at a complicated object, we look at a simple object, which is way simpler, and have one extra rule. And this is just an absolutely amazing idea. Right? So I can just cut it open, and I get a piece of paper. Okay. Hope that is reasonably clear. So let's cut open the annulus. I told you that those two spaces are the same, and you will see it immediately that they are the same. If I cut open the annulus, I take it here, I just bend it open. Right? I just take this edge and pull this a little bit away, and now it's the same space. It's the same identification rule. We just, instead of pulling it like this, putting it together, we pull it like this together. And we can see that in the animation in a second. So here, I can bend it like this, and I get a cylinder. Or I can identify the left and the right edge and it will be an annulus. The animation is not perfect. There will be a hole in the middle. You can't quite see that, but maybe it should be somehow easy to imagine. So I really identify those pictures. And there will be a hole in the middle, but somehow the resolution is not good enough to really see the hole. Yeah, and I would get an annulus. This way I get a cylinder. Whoop, and this way I get an annulus. But they're just the same space, and how can I see that? Well, I get the same space down here with the same rule. I just decide to do the gluing in a slightly different way. So they're really just the same space. And this is a cool argument why they are the same. You just cut them, and you get a square in both cases. And again, square is somewhat much easier to study than an annulus. Hope that makes some sense. And turns out that you can do this with essentially everything, and that's just absolutely fantastic. So let's cut open the swim ring. Let's cut open the torus. I cut it open. Okay, I get a cylinder, and I already know what to do with the cylinder. So I cut it open again. But now what I need to do is I have two rules now. Now I have my bottom edge A, my top edge A, and I want to identify them because I want to get the cylinder. But then I've also cut open the cylinder, so I need to identify the B's again. And this is how it looks like. So let's do this. So we identify the first two edges. That was our little cylinder. And now we need to take it in your hand and bend them together, the one in the back and the one in the front. And this is how it will look like. So you bend them together, and you will get a nice little torus. That's it. Instead of studying a torus, you can study a piece of paper. Okay, so let's do it again. Whoop. So first, identify those two edges, then identify those two edges, and you get a torus. A nice fact, let's do it the other way around. It doesn't matter in which order you do it. You get an annulus. Remember that the animation is not perfect. There is actually a hole in the middle, but it kind of can't quite animate that. But anyway, there's a little hole in the middle. And now you identify, you will see the hole in a second coming up again. You identify the other edges. So there's always a hole, but it somehow only is visible from a certain point onward. You get a torus. That's absolutely fascinating. I think this is absolutely fascinating. So we have now identified a piece of paper with a much more complicated object by just adding the rules. Okay, I have edges labeled A, glue them together. I have edges labeled B, glue them together. And guess what? People use that. So if you're into computer games, for example, this is your screen. And now you imagine you're playing a game on a large world. And usually programmers are very, very sloppy, or kind of a little bit, they make their life easy. And you don't want to run to the end of the world. So they just drop you in at the other side again. And instead of having an end of the world, actually your world takes place on the torus. Because what we have done here, we have identified A and A. So actually, if I walk out here, and you'll see that in an animation in a second, then you will come out in here again. So you can't fall off your surface because the edges are identified. And similarly, if you walk out here, you will come in here again. A little bit nicer. This is a very popular computer game. And it actually took place always on a torus. And we'll see that now running. So if my little spot exits to the bottom, to the top, it comes out at the bottom again. And exits to the left, it will come out at the right again. Yeah? So a very easy way to have an infinite world if you want. It comes out at the bottom again. And essentially every computer game does that. So nowadays computer games are a bit bigger, and you really can't see that anymore but programmers are lazy usually. Check your favorite computer game. Maybe it again actually lives on a torus. I hope that makes some sense, right? So on the right-hand side you see a torus. If you believe this rule of exiting to the left means entering to the right, and if you go out to the top, you come back or from the bottom again. It's an absolutely fascinating idea. Right? So we have reduced the problem, like a quite complicated space, into a much easier problem. Just a rectangle and some rules how you move around the rectangle. I hope that makes some sense. I really love this a lot. So this is kind of a really crucial idea. So absolutely fantastic. Okay, so it worked pretty well for two surfaces. So maybe let's continue. So let's cut open a sphere. Okay, and it's a bit easier to think of the sphere as being a double cone. That topologically is just a really easy operation. You take the south pole, you take the north pole, you pull the north pole up, you pull the south pole down. It gets a bit pointy and you get a double cone. And you can cut that open. I cut open the cone, and what I get? You again get a piece of paper, which now looks like this. I've cut it open, and it would identify, and you can just think of it as like having this in your hand, and you identify it like this. You will get exactly this picture. Right? And it's again just a piece of paper that comes out. And I just split it once further and make it into a rectangle again. Okay. Here the rule is now CC and BB are the same. And if you think of this, as you could just bend them both together and you will get exactly this picture. So what is the difference to the torus? You can now see that this picture is different from the torus because the torus gets the AB. I can write it down here. So reading from here, like let's say in this direction, it gets the AB, but we travel B the other way around. So let me just write B inverse. Then we travel A the other way around. And then we travel B. So the word I get from reading around, and this is the gluing rule because I identify edges, is this one. And for the sphere, it is different. It is, okay, I call it C here. I could have called it A. If you read like this, it's C inverse, B inverse B. Right? So instead of having an AB mixed, you have just CCs and BBs in a row. So you kind of can almost see that they are different spaces. And the annulus was again different. So at this point, you might hope that maybe we can encode absolutely every surface in a little picture like this. And we can. And this is just absolutely fascinating. So instead of looking at surfaces, we can look at pieces of papers and how they are glued together. That's just absolutely fascinating. So let's have a look at another space. So the projective plane is kind of complicated. But if you cut it open, and you just think of it as a half cone, because it is identifying opposite points on the sphere, so I think of it topologically as a half cone, then you can cut it open as follows, and you get the following picture, an AACC. AACC. Okay, so what is different from the sphere? Okay, let's do the sphere again. So if you read along the sphere, oops, this was really bad. Let me try again to read along the sphere. Like this. You get a C inverse, because we run C the other way around, a B inverse and a B. If you read along the projective plane, you get both of them point in the same directions. And now you think of this as taking this into your hand as a piece of paper and try to identify the edges as they are written here. It is really difficult. Huh? So this is really difficult because now this top of this hat needs to go down here. So you just can't do it like for the sphere. That's why this object is so complicated. Just building this out of a piece of paper looks very difficult because this, as I said, let me try to draw it. This end here needs to go down here, and this end here needs to go up here. So how do we even build that in the real world? So very difficult. So somehow this picture already tells us that this space is supposed to be difficult, but now it's very easy. It's just a square with some rules. So here, kind of different from the torus, if you exit here, you will enter here again. Very strange space. Exit to the top, and you come back along the edge A again. A little bit easier as this one. So if you cut open that space, you get something that looks, oh, I forgot the labels. You get something that looks very similar to the cylinder, but note that they are drawn glued to, I have an animation for you in a second. They're glued together in opposite ways. So a point here needs to go down here. While for the cylinder, it was a point here needs to go up here because it was like this picture. Right? A cylinder is really just pop. And now the Möbius strip should be, and then turn it and glue it together. So let's have a look at an animation. Life is boring without animations. You take a piece of paper and just glue it together with a little twist. Bash. And what you get is this funny Möbius strip, which is this one-sided type of surface. And you kind of can see that it's one-sided because kind of the brown and the, greenish region will be the same. So let's do it again. You take the piece of paper, and instead of doing it in a cylinder, you do it in a little twist and glue it together. There you go. And we have reduced, let's compare with the cylinder again. For the cylinder, here's my torus. Let's go back to the cylinder. For the cylinder, we essentially do the same, but we don't twist, right? We just glue them together as they are, like this or this. And for our little, where is my Möbius strip? For our little Möbius strip, you just do in this one twist. And you can build this live. You can really, if you take a piece of paper, it should be very long. Like in this animation, you can really just build them in the real world. Okay. And it's just encoded in our little picture here. And it's just really fascinating. Right? So here it goes up and down. So you twist them, meaning you identify a point at the top with a point at the bottom. In other words, kind of in contrast to the cylinder now, if you exit here, you will enter here. That's what the rule tells you. Always identify them along the orientation that you see. And again, it's a much easier picture. It's just a square with a rule instead of a very complicated object. So let's do the next one. The Klein bottle. In case you don't remember what the Klein bottle was, it was this funny space here, where the ants kind of, where outside and inside are kind of the same. So let's see what we can do with this funny space. So if I just did it the other way around now, I just glue instead of cut. It's a kind of reversible operations. And you can see it almost looks like a torus. So a torus would have this guy, this guy points down, this guy points up. Remember on a torus you would do this and coming out at the other end again, but now it's twisted, so you come out here instead. And that's the picture of the Klein bottle. So you just take a cylinder. I have a slightly better picture in a second, but you take a cylinder, but you now need to identify those edges twisted, so those little circles twisted, and that's why this thing happens. So let me pull up a slightly better picture. I didn't find a good animation, but I have a nice picture. So you first just make it into a cylinder. Right? You identify blue, but then you need to identify green in the opposite way. And the only way to do this, you need to glue them together in the correct way, is to kind of push it like this. And that's why you get this, this funny looking space with this kind of little self-intersection here. Yeah, so for a torus, I would just identify green and green, and it would just give me a torus. But now I need to identify them kind of twisted, and the only reasonable way to do this is kind of doing this trick. And let's compare. So here, it is really the same space. It just, so here, it's turned around. So that's why. So you have a cylinder, but you now need to identify the ends twisted. So you end up with this little space here. Okay. And again, this is not really clear how to do this actually in 3 space. So in my animation, or not in animation, in the graphic, it was self-intersecting. So this is really, again, kind of an object that doesn't really naturally want to live in 3 space. But if you just think of it like this, it's clear that it is a surface, because here is your disk. It's right in front of you. And there's just a rule how to glue the ends of the disk together if you want. And this is really a fascinating picture. So let's just do it once more. So here, and now let's have a look at the kind of the different things you see. So this is AB inverse. So I read around like this. I get B, A inverse. So A is run, sorry. B and A, and then B inverse and A again. So BA, B inverse A. And yeah, and for the torus, almost the same, but slightly different. For the torus, I would do not this one, I would do this one. So AA, BB. So if I read it again like this, I get BA inverse, B inverse, A inverse, A, sorry. And this is almost the same, right? Note for the Klein bottle, you have this funny twisting, and you see that in this word that I write down, because those symbols appear kind of with the same power. And the non-twisted ones always have like those. That's how it works. So the difficult ones are the ones with repeated symbols with the same orientation on the edges. Because if you take this in your hand, you would kind of need to twist them together, like for the Möbius strip. Let me pull up the Möbius strip again. Right, so here the edges have the same. And that's why you need to twist them and put them together. And whenever you need to twist something, it's always a bit difficult. So let's go back to our little Möbius strip. Right, so they have point in the same direction. So if I write down the word, it's like, let's say we are again going in this direction, it would be AA. And that's exactly kind of the difficulty. And turns out that there's a really beautiful description. So all surfaces where you never have this appearing, they appear in the real world. And all surfaces where you have this appearing, they don't appear in the real world. Kind of and a really easy way to kind of have two different classes of surfaces. Okay, I hope this was reasonably clear. We are cutting down spaces into much smaller spaces and easier spaces, namely rectangles in this case. But you somehow remember, keep this little computer game picture in mind. You remember what was glued together before. So if you exit, you will enter again from the opposite edge. And this is an absolutely fabulous step, because now instead of looking at those slightly complicated objects, we can look at squares and rectangles or a little more general polygons. Yeah, so polygons instead of, so here are polygons. Polygons instead of surfaces. And always what you see is always a local neighborhood. It's always a disk. And here are my polygons. And they sadly have the same notation as the cycles. But if you want to think of the endpoints as being part of a graph, that these are really just the filled-in graphs. So here would be our cyclic graph, C2. And I just put a disk in the middle. The next one is a cyclic graph, C3. And I just put bash, a disk in the middle, and so on. So that's why they're also denoted by Cn, just plus a disk in the middle. Right? And that's it. And that's what I call a polygon. It kind of makes sense to call it a polygon. And it turns out that all surfaces can be described using polygons only, one polygon only. And that's just really kind of the statement we are up for right now. And then if we understand that step, that all surfaces are given by polygons, then we can try to classify them, because then it's like only a kind of a Euclidean type combinatorics of just staring at polygons, which is somewhat much easier than trying to imagine high-dimensional spaces. I hope that makes some sense. Okay. And I call these, well, whatever, 2-gun, 3-gun, 4-gun, 5-gun, 6-gun, M-gun, if it has M sides. Right? Hope that makes sense. The polygons itself, they are also surfaces. They are just disks. Right? Everyone is just a disk. But I somehow like to remember that they have vertices and edges, and they have one face, namely the one that stares at you. So here's your face. There you go. It just stares at you. It's a disk itself. Okay. Hope that makes some sense. And what we do, so motivated by what we have seen, well, we want now a polygonal decomposition of a surface. I will show you some examples in a second. And we will just do the following. We just cut it open until we get polygons, and we have gluing rules on polygons. And here's the formal definition. But it's a bit nicer to just look at examples. But I think I have one more here. Let's just go through a few comments. So what we really want to do is we want to take an arbitrary surface, cut it open until we get polygons, and then we have a bunch of polygons, and we only remember how the polygons are glued together, which is, I hope I convinced you, much easier than trying to study the surfaces itself. Turns out it's equivalent, which is kind of really amazing. So it looks like it's much easier, and it's definitely much better for humans, but it somehow is still equivalent as a problem, which is fantastic. So we just do it, and somehow get rid of all complications of staring at complicated surfaces. Always keep the surface picture in mind. So when I will show you, like, from now on, we will see like 1 trillion polygons. And you should always think of them as you take them in your hand and you identify the corresponding edges. But kind of combinatorially and in practice, it's just somehow much easier to show you kind of a plain picture instead of showing you something complicated that potentially lives in a high-dimensional kind of in R4 or something in a high-dimensional space. Okay, and the only really information beyond what I just waffled a little bit that you should take away from this slide is that we now can, whenever we have such a decomposition, we can say a surface has vertices, edges, and faces, very similar to our graphs. We are now one dimension up, so we have faces as well. And what are the vertices, the edges, and the faces? Well, the vertices are the vertices of the polygons, the edges are the edges of the polygons, and the faces are the faces that I glue in the middle of the polygons. And we can use graph theoretical methods to study a higher dimensional object, which is an absolutely fantastic idea. I say it again, absolutely fantastic idea. So we reduce the problem. So let's say we can pull this off, and of course, spoiler, spoiler, we will be able to pull this off. Then we would have reduced the problem of studying surfaces essentially to a version of studying graphs, which is somewhat like 1 trillion times easier. I hope that makes some sense. Okay, and I will show you an example. How do I have an example on this slide? No, we go back to this in a second. So what I will draw is I will draw those pictures. Okay, and I do this with some code, so they will always come out like this. And the identified edges are always the pairs, so they always come in pairs. You never have 3 of them. I will explain that in a second as well. So you either have one, these are the ones that stay open, so like B and C. You don't do anything with them, they just stay where they are. Or they come in a pair, and then they are identified. So our little annulus was exactly this picture, where you take bottom and top. Maybe I can just try to draw it, and glue them together. And you can just read this off from this little diagram. So I've encoded everything in this diagram. The orientation tells you how to glue things together, and the labels tell you what to glue together. Okay? And I also use colors to make it a bit easier, but the colors are just kind of a visual aid. So you always glue together edges of the same color. Note that I'm following the standard literature, but we really don't need the orientations on the. So we have 2 types of edges. Edges that appear twice and edges that appear once. We need the orientation for the edges that appear twice because it tells us how to glue things together. If I draw the same one, do I have it actually? I probably do have it. The Möbius strip. If I draw the same picture, it almost looks the same. But note that the orientations on the arrows A are swapped. So the orientation tells me whether I glue in a twist or not. But the orientation on the single edges, like B and C, doesn't really play a role. I just put it there because that's kind of the standard notation. Okay, anyway, so this is what I will draw. And all the information of the surface is encoded in this little picture. It's absolutely amazing. Think of it as taking it in your hand and identify edges of the same with the same label. And that's the surface. And that's called a polygonal, here's the jargon again, it's called the polygonal decomposition of a surface. Because in the end, I only have a polygon to stare at. Right? I hope that makes some sense. And I listed all of them the standard ones here, so we can compare them. They all fit on a square, but they are slightly different. As you can see, the combinatorics are slightly different. Here's our torus. You glue together those edges, remember the animation, and then you bend up this one. Compared to the Klein bottle, the orientation tells you that those two spaces should be different, because one of them has, look at the edge A, has this little twist inside. So here my A's go both in this direction, and here my A's go like this. Right? And similarly, you can just look at other pictures. Okay, and if you're looking at the most complicated space, here's another picture of it. So our little friend, the projective plane, or maybe our little enemy, the projective plane, not sure. But now take this polygon, just try that at home. Take a piece of paper and try to glue it together using those rules. That's essentially impossible, which kind of tells you why this space is so difficult. So you need to put in a twist for B and for A. Right? So if you just put in a twist for A, you get the Klein bottle, which is a bit easier. But now you need to twist both, and this is kind of this slightly more complicated space. Okay, I hope that makes some sense. And let me pull up the previous slide again. So that's what I do. It's just the recipe what I will do, what you have just seen. I label the edges with letters, and there are some colors, but the colors, you can just follow the labels. And the colors are just helpful. And the direction gives me the gluing rule. So I have a labeled polygon where edges are labeled A, B, C, whatever, and there will be some direction corresponding to whether you glue them together, twisted or not. And what we do is we just identify them along twisted edges, along edges of the same label. Here again, a few of these spaces. So what you can build at home, the annulus is really, really simple. You probably have done that at one point in your life. You take a piece of paper and identify two edges. The sphere is also very simple. You take a piece of paper and you bend it into a cup. Essentially, that's what this is saying. The torus is also not very difficult. You just need a very long piece of paper, and it's kind of easier to do. And the other spaces are difficult, but the Möbius strip is doable. And they are all difficult because, again, all of them have a twist. And the one that has a double twist is a projective plane. It's the most complicated one you see on this slide. So in some sense, the number of twists you need to do is kind of how hard it gets to imagining those spaces. But still, I pointed out again, this is a much cleaner picture, right? I just draw a few polygons for you, and I tell you how to glue them together. And okay, now the projective plane makes sense. It's just one of those guys. I hope that makes some sense for you. Cool. Okay, so let's just list some facts, and let's do some funny operations on those spaces. Okay, so every polygon is a disk, right? That's what I said. So where's my disk in my picture? You ask, it's a polygon you see. Where's the face? It's a polygon you see. And why do we never have, so we only have single edges, they just leave them alone, they're the boundary components, or you have double edges that you glue together. Why do we never have edges like AAA, right? Three edges with the same label. Well, if you glue them together, you would get this picture, right? So you would have three edges, and now you need to glue them together, and that's exactly not a surface. So the surfaces are the kind of the spaces, the two-dimensional spaces, where you only have two labels, and never higher labels. So you never get those book pictures. You only glue together two things. I hope that makes some sense. And we won't do that, but you can always kind of cut the polygons even finer, and then have sort of triangle is actually enough. So you can encode all surfaces just using a triangle by cut the spaces even finer. So we will sometimes do that. But this is ridiculous. This is a fantastic statement. So the triangle is somewhat enough to get all surfaces. Just the triangle. Easiest kind of non-trivial polygon that you would see. Right? So we can somewhat, if we want to, we can cut the surface into many, many, many different pieces and kind of make the pieces itself easier, if we want to. And we get different polygon decompositions of the same surface. We'll see some of them. So the main difficulty will be the following. So it's kind of fairly straightforward to see that every surface has a polygon decomposition, but then one surface can have many. So we kind of need to decide from the polygon decomposition what surface we see. And that will be kind of our main task, and it has a really nice answer. It just takes a bit to answer it, right? So we have many decompositions of the same thing, essentially because you can somehow cut everything finer if you want. But always cut things even finer, right? You can have smaller and smaller and smaller disks if you want. Okay. Okay. So here's a way, for example, to get a polygon decomposition of, so the space I have is just the annulus. It just has a hole in the middle, and you can just making kind of that's essentially the argument why you get a polygon decomposition. But you can do even better. You can just find one and reduce it to just one. So we'll see how that works. So here's my space. Well, it is the annulus. It's just drawn a little bit less smooth, but in topology we can do that. So I just have this surface here, and I can cut it open and then just bend it open, and I would get my polygon decomposition, which is just one polygon. But here you have a polygon decomposition with more polygons. Same space. One is sufficient, but we can have more of them. Okay, so let me show you essentially some of those moves that we're going to do, and the jargon here is surgery. So what is the goal? We would now try to understand surfaces using pieces of papers. So we kind of need to understand the ways to move around pieces of papers, which kind of preserves our surfaces, because there are many polygonal decompositions of the same surface. And the tool to do so is called surgery. And it's essentially a cutting and gluing thing. So we'll see how that works. And essentially what I would like to do is I just show you an example. Okay. And the surgery just has two rules, so it's not so bad. But let's go with an example. So our torus is really just this space. I hope that makes sense now. So where we identify bottom and top in the straightforward way, pulling it around. So what could we do? Well, take that space and cut the piece of paper along C. Well, that's a cutting operation. So what happens if you cut the piece of paper along C? So you have now a little square. Maybe I can draw it. So you have your little square, okay, which represents the torus, and I cut in a little bit into the square and pull this edge to here and pull this one to here. So I get a space where I have now green and green opened up and kind of the thingy around here. So I just cut a little bit in and I pull it off. Yeah, and it looks now like this. That's exactly what I've done. So cutting in, if you identify them back together, you squeeze them together, you get exactly this picture. And that's an operation. So what you see here, this is the torus, and this is the torus as well. I hope that makes some sense. So they're different pictures for the same object. And if you take this one into your hand, this one is hopefully clear by now. If you take the other one into your hand, what you can do is you can just smash C first, and you get this picture, and you know what to do from there on. I hope that makes some sense. And you can continue. Arbitrary, we can, for example, now cut in an edge. What is the color here? D, like cutting in here. You get the D. And to get another polygon decomposition of the surface. And you can cut and cut and cut and cut. And you get many of those polygon decompositions. So what we need to do eventually, and we will get there very soonish, it's a beautiful answer, I promise you, is if I give you this picture, eventually I will give you this picture, and I will ask you, or we need to ask the question, what space do we see? So how can we determine what space it is? Well, there's one way. We build it out of paper. But as mathematicians, we kind of want a smarter way of doing it. Instead of, well, building out of paper is fun, for sure. But there should be a smarter way of deciding what kind of space we see. And there will be a completely combinatorial way to just look at the polygon, count a certain type of things, we'll see how that works, and decide what space you see, which is an absolutely fabulous answer to the main question how to understand surfaces, because there's just an algorithm from some polygon that spits out the answer. This is a torus, or this is a whatever Klein bottle, or a sphere, or anything, essentially. And that's just, it's absolutely fabulous. You reduce the problem to a two-dimensional problem, studying polygons, but you also can just precisely tell what polygon corresponds to what. I said again, we can't do that right now. We will be later on. Right now, I just show you that everything kind of give you some examples of polygon decompositions. Okay, so you can also cut in like this. So take the polygon and you cut here. What will happen if you cut the polygon along the edge E? Well, the following will happen. You will have two pieces of paper in your hand, right? If I cut along E, I will have two pieces of paper in my hand. Let's do this. Or you can do it like this. I did it the other way around. That's fine. So if you cut along E, you can also just do it like this. You get another edge E. You cut along B. You get another edge B, and so on and so on. Okay. So we end up in the end with something that looks very different, kind of a sequence of cutting moves, and even with two polygons. So let's understand this decomposition down here. So what I'm saying, and it's not clear why there should be a torus anymore, right? But it is. And so we need a way to figure it out why it is. So how does this work? So okay, I exit at C, so I enter at C again. That's kind of fine, but now comes the fun. If you exit at F, you enter here. So this is actually a connected thing. Also, it looks disconnected because it's connected via jumping around F. And here, if you exit at A, you come in at A again. So it's really connected. If you exit at D, you come in at D, and so on. Exit at E, you come in at E. And the question that we try to address in this lecture is, if I just give you something like this, how can we decide what kind of surface we see? Because that's essentially the question we need to answer. We can associate to every surface a polygon. And what we need to do is, can we go back? And the study of polygons is just so much easier than the study of surfaces. But it's equivalent, which is kind of the magic. Let me see whether I want to do the next slide. Exactly, that's what I just said. Very good. The slides are smarter than me. That's very good. Right? So, question, what can we do if I give you this picture? Can you do anything? Well, so the first thing you can check is that this is connected. Also, it looks disconnected. You have two polygons. But let's say you exit, what is my favorite here? You exit at G. So where's the other G edge? The other G edge is here. So you come in via G again. So this is a connected surface. But which one is it? Right now, we can't really decide. And the whole task of, so we can't, right? So I'm saying, if you are thinking now, I don't know what the surface is, that's okay, because right now we can't decide what it is. I will tell you a rule how to do this, a beautiful rule, but right now we can't. So the obvious task is find a rule to go from polygons to surfaces, because what I told you today is exactly the opposite. So let me pull up my animation again. I told you how to go from surfaces to polygons. So here's my torus. Very good. So how to go to a polygon, you cut the torus like you would maybe cut a donut or something. So you cut it, you bend it open, and then you cut it once more, and you bend it open flat into a picture. So going from a surface to a polygon is not so difficult. And in order to reduce the whole study of surfaces to polygons, we need to go back. And that's essentially what we are going to see in the remainder tomorrow and next week. But I promise you there will be a really beautiful answer. In the end, you will be able to decide by just looking at this picture what surface you see. And then our whole problem of classifying surfaces is just looking at polygons and, well, count a certain number of things. But anyway, I'm done for today, so thank you so much for coming.